A warm welcome to one and all watching this video. I'm Jenita Christy, Assistant Professor in the Department of Computer Science and Engineering, Bharat Institute of Higher Education and Research. Today, we are going to see the topic number system and codes. So, first we'll see what are all the number systems available. So, binary numbers, octal numbers, hexadecimal numbers, and then decimal numbers. So first, if we see the binary numbers, the binary number, its base is 2 and its digits are 0 and 1. So as its base is 2, it follows 2 digits that are 0 and 1. And then if we see the octal numbers, its base is 8. So we have 8 numbers. So it starts from 0 and then it starts from 0 to 7. Likewise, hexadecimal numbers, its base is 16. So here the digits are 0, 1, 2, 3, 4, 5 till 9. And then instead of 10, we have A. And then 11, we have B. It goes on like this. So for 15, we have F. So the hexadecimal digits are 0 till 9 and then A to F. So we'll see each and every conversion with an example. So here we have a question that is a decimal conversion. So here we have a binary number that is 11010.11. This binary number has to be converted into a decimal number. So what we are going to do, see here, first we'll take this part, the real part. So the first digit is 1. So take that 1. So if we see here, this position is 0, this position is 1, 2, 3, 4. So this position is 4. So the digit is 1. So 1 into 2 to the power 4. So what is 2? 2 is nothing but the base of the binary number. So 2 to the power 4. So it is nothing but the position. So this position is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. So here we have 1 into 2 power 4. Likewise, for the next digit, that is also 1. So 1 into 2 power 3, because this position is 3. That is 2 power 3. So likewise, here's 0. So 0 into 2 power 2, 1 into 2 power 1, and then 0 into 2 power 0. That's what we have written here. 1 into 2 power 4 till 0 into 2 power 0. Now, here we have, after this decimal point, here we have 1, 1. So the position of this particular 1 after the first digit after the decimal point is 2 power minus 1. Here it is 2 power 0, 2 power 1. When it comes here, so this is 2 power minus 1 and this is 2 power minus 2. So what we have written here, 1 into 2 power minus 1. And then for this one, here we have 1 into 2 power minus 2. So when we calculate each and everything, we'll get the result 26.75. Okay, this is what we do from a binary to the decimal conversion. Next, octal conversion. So from an octal number that is given, that is 127.4, we are going to convert it into a decimal number. So as we all know, the octal number, it ranges from 0 to 7. So here we have, if you see this number, it is less than 8. So take the real part, that is 127. So the position of 7 is 8 power 0. What is 8 here? 8 is the base of the octal number. So the position of this 7 is 8 power 0, 2 is 8 power 1, and 1 is 8 power 2. Likewise, 4 is 8 power minus 1. So when we calculate this 1 into 8 power 2, plus 2 into 8 power 1, plus this 7 into 8 power 0, plus 4 into 8 power minus 1. So when we calculate this, we get the answer 87.5 to the base 10. Likewise, the last, the hexadecimal number. Here also we have converted a hexadecimal number into a decimal number. So as we all know, after 9, the hexadecimal number, it goes on like A till B. Sorry, A, B, and then till F. So here we have B. So B, it means that its equivalent is 11. So here we have written 11 into 16 power 3. Because this F position is 0, 5 position is 16 power 1, 16 power 2, and 16 power 3. So 11 into 16 power 3 plus the next digit 6. 6 into 16 power 2. Next is 5. 5 into 16 power 1 plus 15. F is equivalent to 15. So 15 into 16 power 0. So we get the answer 46,687 to the base 10. So let's see this tabular column. So the first column is decimal number, next is binary equivalent to this decimal number, and then octal, and then hexadecimal. So first is the decimal number. So for 0, the binary equivalent is 0. Likewise, octal and hexadecimal also 0. And then for 1, binary is 1, octal is also 1, hexadecimal is also 1. When we take for 2, the binary numbers, it consists of only 0 and 1. So for 2, the binary equivalent is 1, 0. Whereas in octal, it is 2 and hexadecimal, it is 2. So till 3, 4, 5, 6, 7, 7, it's same because octal and hexadecimal are same till 7. And then if we see the binary equivalent, for 3, it is 1, 1. And for 4, it is 1, 0, 0. And when we go here after 7, for 8, is there any decimal number 8? Yes, we have. So its equivalent is 1, 0, 0, 0. So after 7, the binary equivalent is 4 bits. Till 7, it is 3 bits. And after 7, 4 bits. We can represent the binary equivalent with 4 bits. So when we see the octal equivalent of 8, actually octal number ranges from 0 to 7. And if we see the octal number for 8, it is 1, 0. So 0 is the answer and 1 is the carry. So the equivalent of 8 is 1, 0 in octal number. And then 8, 9 is there in hexadecimal. And for 9, the octal number is 1, 1. So here, this one is the extra number that is the difference that we get between 8 and 9. So the difference is 1. So that is the 1 here. And this 1 is the carry. So whenever it goes beyond 1, the carry is 1. So next is 1, 0. So for 10, we'll see what is the octal equivalent. So if you see here, the difference between 10 and 8 is 2. So here we write 2, that is the difference, and then 1. So when an octal number, it is greater than 8 and less than 16, we write the carry as 1. When it goes after 16, we write the carry as 2. I think it's clear. So next we'll see 14. Okay, 14. If you see 14, the octal equivalent. Okay, what's the difference between 14 and 8? That is 6. So we'll write 6 here. And then next, carry 1. Why carry 1? Because the 14, it ranges between 8 to 16. So here we have 1, 6. And then again, the octal number, the last one, that is 16. Okay. If you see here 16, we have the octal number 8. So octal number 8. So if you see here 1 8 is 8, 2 8s are 16. So here also we have 16. So the answer is 0. and then the carry is 2 because 186, 2 8s are 16. So we have 2 as the carry. So if you look at the binary equivalent of 16, so till 7, it has 3 digits, and after 7, it has 4 digits, and after 15, the representation of the binary digit, it can be of 5 digits. Okay. So here, if we see here, A till 15, that is 10 till 15, we have A to F. And then for 16, again, we have 1, 0. 1 as the carry and 0 is the sum. So once you have learned about this binary number, octal number, and hexadecimal number, we are going to perform the arithmetic operations in these numbers. So first we'll see the binary arithmetic, that is addition, subtraction, multiplication, and division. So we'll see the example here for addition. The organ we have 1 0 1 0 1 1. The added we have 1 1 0 0 1. So what we are going to do, we are going to add it. So first, starting from the least significant bit, so 1 plus 1. So when we add the binary addition, when we add the binary digits, 1 plus 1 is 0, and then carry is 1. It's like when we add 1 plus 1 in decimal numbers, when we add 1 plus 1, it is like 2. So what is the binary equivalent of 2? 1 0. So we put 0 here and then the 1 as a carry. Okay. Now 1 0 and the carry 1. So again we add 1 plus 1 plus 0. So that is again 2, and its binary equivalent is 1 0. So we put 0 here and then 1 here. So now 1 plus 0 plus 0, that is nothing but 1. So 1 plus 1 is 0, 1, carry 1. Well, again 1 plus 1 is 0, again carry 1. 1 plus 1, 0, the carry 1. Yes. So addition, we got the answer 1 0 0 0 1 0 0. And then the subtraction. So in subtraction, we have the minuend 1 0 0 1 0 1 and the subtrahend 1 1 0 1 1. So first we are going to subtract 1 minus 1, that is 0. Okay, very simple. And then we'll move here. Here we have 0 minus 1. So 0 is less than 1, so we can't subtract. So what we have to do, we have to borrow. So what we are going to do, we are going to borrow from the previous number. So here we have 1. So when this 1 has been given here, okay, so it becomes 0. So actually, as these digits are binary, these numbers are binary numbers and its base is 2. So we see here 1 will be given here. Okay, so in the sense 2 will be given here. So the binary equivalent of 2 is 1 0. I repeat, here we have 0 and then 1. We are going to subtract. We can't subtract. So what we have to do, we have to borrow. So when we borrow, here we have 1. So when it gives something to here, it gives 2. Why it gives 2? Because its base is 2, it gives 2. And the binary equivalent of 2 is 1 0. So that's why we have written here 1 0. And then because it is given here, so this will become 0. So 1 0 minus 1. So usually what is this 1 0? 1 0 is nothing but 2. So 2 minus 1 is 1. So here we have 1. And then here we have 0 minus 0 is 0. Again, 0 minus 1. So we are going to borrow from here. So when we borrow from here, it gives 2 here. And then 1 has been given here. Okay, 2 has been given here. So it becomes 1 0. So 1 0 is nothing but its equivalent is 2. So 2 minus 1 is 1. So 1. And then here we have 1. So 1 minus 1 is 0. Here also we don't have anything. 0 only. So the answer is 1 0 1 0. When we go to multiplication, we have the multiplicand and the multiplier. So it's very simple. Multiplication 0 0 means 0. 0 1 means also 0. And then 1, when we have 1, when both the digits are 1, we have 1, otherwise 0. So here we got the answer as 1 0 0 0 0 0 1 0 0 as the product. And the division, the dividend we have 1 1 1 1 0 1, and the divider we have 1 0 0 1. So we are going to take 4 digits and we are going to see whether that is greater. Yes, 1 1 1 1 is greater than 1 0 0 1. So now we can proceed by taking the first 4 digits. So 1, it will go in 1. So 1 0 0 1 we write here, and then 1 minus 1 is 0, and then 1 1, and then here we have 4 digits, here we have 3 digits, and we add 1. We have to check whether this 1 1 0 0 is greater than 1 0 0 1. Yes, it is greater. 1 1 0 0 is greater than 1 0 0 1. So what we do here, we are going to again do this, that is 1. So 1 0 0 1. Now what we have to do, we have to subtract it. Yes, it will become 1 0. So 1 0 minus 1 is 1. Here we have, so when we borrow from here, so here we'll have 1. Here we have 1 0. So here this 1 will become 1 here, and this 1. So the remainder is 1 1 1, and the quotient is 1 1 0. So this is what is the binary arithmetic: addition, subtraction, multiplication, and division. Next is the octal. So octal arithmetic. So here also we are going to see addition, subtraction, multiplication, and division. So in the octal arithmetic, we have 5 4 7 1 3 7 5 4. Okay, the augend and the addend. So here we are going to add. So when we add here, the sum should be less than 8, because we know the octal number ranges from 0 to 7. So the sum should be less than 8. So when it exceeds 7, we'll see what we are going to do. So now we'll see this with an example. So 5 4 7 1 and 3 7 5 4. So 1 plus 4. 1 plus 4 is 5. Next. No problem. 5 is less than 8. So no problem. Okay. And then 7 plus 5. 7 plus 5 is 12. Okay. That is greater than 7. So what we are going to do? So now we are going to see the difference between 12 and 8. What's the difference between 12 and 8? That is 4. Okay. So that is 4. And then the carry is 1. Because the number ranges between 8 to 16. 1 8 is 8, 2 8 is 16. Okay. So the number ranges from 1 to, sorry, the number ranges from 8 to 16. So the carry is going to be 1. If it exceeds 16, it's going to be 2. So here we have 7 plus 4. I repeat, 7 plus 5 is 12. So we are going to see the difference between 12 and 8. Why we are seeing the difference between 12 and 8? Because 8 is the base. So the difference between 12 and 8 is 4. So we write 4 here, and then the carry is 1. So next, 7 plus 4. 7 plus 4 is 11, and then again we have a carry, so 12. Again we got 12. So nothing but it's simply 4 is the sum, and then 1 is the carry. Now 5 plus 1 is 6. 6 plus 3 is 9. So now see what's the difference between 9 and 8? That is nothing but 1. So write the difference. That is the sum 1, and then the carry is 1. So this is what is the octal arithmetic in addition. Next is the subtraction. So here we have the subtraction. The digit is 7451 5643. So the first, here we have 1. Yes, 1 is less than 3, so we can't subtract. So we are going to borrow. So we are going to borrow from here. So the 5 becomes 4. And then when it gives, here it gives 8. Yes, because it is an octal number. So when we borrow, it gives here 8. So 8 plus 1 is 9. So 9 minus 3 is 6. So write the 6 here. So 4 minus 4 is 0. And then here 4 is less than 6. So we can't subtract. So we are going to borrow. So we are borrowing from here. So 7 becomes 6. And then it gives here 8. So 8 plus 4 is 12. So 12 minus 6 is 6. And then 6 minus 5 is 1. So 1606 is the difference that we got. Next is the multiplication. So the multiplication, the multiplicand, we have 326 and the multiplier, we have 67. So here we are going to see the multiplication. So 6 into 7. So 6 sevens are 42. So 6 sevens are 42. So what we are going to do here, this is the octal multiplication. So 6 sevens are 42. So what do we do here? We are going to see, okay, 1 8 is 8, 2 8s are 16, 3 8s are 24, 4 8s are 32, 5 8s are 40. So see here, 5 8s are 40, 6 8s are 48, that is greater than 42. So stop here, that is 5 8s are 40. So now see the difference. So 5 8s are 40 and the answer we got here is the 6 7s are 42. So the difference is 2. So write the 2 here and then 5 here. Yes, is it clear? 5 here. So 2 sevens are, next 2 sevens are 14. And then again we have the difference as 5. So it becomes 19. So 1 8 is 8, 2 8s are 16. So the difference between 19 and 16 is 3. So write 3 here. And then next 1 7 7, 2 7s are 14, 3 7s are 21. So 21. So if we see the 8 table, 1 8 is 8, 2 8s are 16. So we write the 7 here and then 2 here. Likewise, 326 into 6, we got 2404. So we are going to add here. So when we add here, we don't have any problem in addition. That is 2, 7. Yeah, everything are the octal numbers. Okay. Now, the division. So the division we have 7514 and the divider we have 63. So 163, 63 and the difference we have 114 and then again 163, 63. The difference we have 6364 and then 4 we have 314 and the remainder is 40 and the quotient is 114. So this is what is the binary digits and then the conversions and then the arithmetic operations. Now we are going to see the base conversions from one conversion, one base to the other base. So we have the series of substitution method. So we have a polynomial representation. N is the number. So here we have a to the base n minus 1 into r. R is the radix. N is the number of digits in a number. So it starts with n minus 1 and it goes on like this. So till r power 0. And then after that decimal point, we have r to the power minus 1 till r to the power minus m. So this example, we already have seen that. So conversion procedure, we have to start from base A to base B. So we'll see this with an example. So here we have a binary digit 11010. So this binary digit, we are going to convert it into decimal number. So there is no decimal point here. So this position is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. So it goes on like this. And then we got 26 to the base 10. Next is 627 to the base 8. So octal number into a decimal number. So this position is 8 power 0, 8 power 1 and 8 power 2. So here we got the answer 407 to the base 10. And then now we'll see the conversion from the decimal number to the octal number. So the conversion from the decimal number to the octal number, that is 315 to the base 8. So what we are going to convert, we are going to process with that particular base. So we are going to convert it into a octal number. So the base is 8. So calculate this with 8. So when we do this, 3 8s are 24 and 4 8s are 32. So we'll go with 3. So 3 8s are 24. So what is the difference between 31 and 24? That is 5. So that is 55. So here we have 39, and then again it goes on with 8. So 4 8s are 36 and the difference is 4. Here we write the difference 3 7 4. So when we write the answer, we'll start it from the last. So the 0473 is the answer. Next, from the decimal to the hexadecimal. So 315 to the base 10. So as I've already said, to what we are going to convert, we are going to process with that base. So we're going to convert it into a hexadecimal number. So we are going to process with that particular base. That is 16. So 315, 16. So when we see here, 1 16s are 16. So when we see the difference, that is 7s, that is 75. So 9 16. So the difference is 3. Likewise, here we have 1 16s are 16, and then the difference is 3, and the difference is 1. So when we start from the last, the answer is 13B. Another example, here we have a decimal point. So after decimal point, how we are going to process? The number is 0.479 to the base 10. So what we are going to do? So we are going to convert it into a octal numbers. So what we have to do, we have to process with that particular base, that is nothing but 8. So take the question, that is 0.479 into 8. So here we have the answer 3.832. So when we take the next time, we leave this real part, we'll take the fractional part alone. So that is the decimal point. After decimal point, we have 8.832. That is 0.832. So 0.832 into 8. So here we have 6.656. And then again, when we take 0.656 into 8, that is 5.248. So at last, okay, after some 4 or 5 iterations, we are going to stop it and we are going to write the answer. So when we write the answer, we are writing it from the top. So write it as 0.3652. We take only the real part. Likewise, the next example is the conversion from the decimal to the binary. So binary, we know the base is 2 and we are going to process with this 2. So take the question, that is 0.479 into 2. So here we got the answer 0.9580. And then take the fractional part alone, that is 9580 into 2. So when we multiply, we got the answer 1.9160. So at last, some iterations, we're going to stop it. Okay, here we have stopped with 4 iterations. And then from top, you would start writing the answer. So that is 0.0111. So we'll see what we are going to do in the conversions. So when b is equal to a to the power k. So to convert a number from one base to the other base, and when base b is equal to a to the power k, whereas k is nothing but a positive integer, what we are going to do, we are going to form a group of digits. And when we form a group, in each group, we should have k digits. And we are going to form it in both the directions. Okay. After the decimal point as well as before the decimal point, we are going to start forming group. Each group consists of k digits. And from the radix point, and then what we are going to do, we are going to replace each group with the equivalent digit in base b. So to convert a number n from base b to base a, so when b is equal to a to the power k and k is a positive integer, replace each base b digit in n with equivalent k digits in base a. So we'll see this with an example. In the first example, here we have 001, 010, 111.100. So this is the binary number So here we have, after the decimal point, here we have 100. So what is this? What conversion is this? This conversion is from the binary to the octal. So octal, yes, octal, its base is 8. And then how we got this 8? 2 power 3 is equal to 8. So 3 is nothing but we are going to form 3 bits in a group. So after decimal point, yes, we have only 3 digits, no problem. So 100 is one group. And then before decimal point, we'll start from here. So 111 is one group. The next group is 010, and the last group is 100. So when you group it at the last, like when one digit is there or 2 digits are there, and one digit, if any digit is missing, to make it as 3, you can add 0. No problem. Here also you can add 0 if any digit is missing to form a group of 3 bits. So what is its equivalent? So its equivalent is 100 is nothing but 4. 111 is 7. So we write 7 here. 010 is 2. And then 001 is 1. So 127.4 to the base 8. Next example, that is the binary to the hexadecimal. So when we convert from the binary to the hexadecimal, so the base of the hexadecimal number is 16. So how we got this 16? 2 power 4 is equal to 16. So we are going to form a group which consists of 4 bits. So start from here. So 1111, 4 bits. So one group. 1010, yeah, another group. Likewise, it goes on. So we got 4 bits. So we're going to write the hexadecimal equivalent. So what is 1111? It's nothing but 15. As we all know, there is no 15. So what we are going to do, we are going to write it as F. Yes, the hexadecimal equivalent for 15 is F. So 0101 is 5. 0110 is 6, and then 1010 is B. So computer codes. So we'll see what is a code. A code is nothing but a systematic use of a given set of symbols for representing information. Or to represent the information, we sometimes use code. For example, the traffic lights, what it represents, the red represents stop, like that. So in computer also we use the different codes. So fixed point numbers. So what is this fixed point numbers? It is used for signed integers and signed magnitude. 2's complement or 1's complement system are also used in order to represent the sign for a particular number, whether it is a positive number or a negative number. We use the sign magnitude. So if you take an integer, first is the sign bit, and then the magnitude, and then the implied radix point. So if it is a fractional number, first is the sign bit, second is the implied radix point, and the third is the magnitude. So we have the excess or biased representation. So an excess K representation of a code C, add K to each code. So if it is excess K representation of a code means we are going to add K to each code word C. So it is frequently used for exponents of floating point numbers. So excess 8 representation of a 4-bit 2's complement code. So we have the excess 3 code, we have the excess 8 code. So in order to represent the codes. So we'll see binary coded decimal, that is nothing but the BCD. It is used to represent the decimal digit 0 to 9. BCD means it starts from 0 to 9. So 4 bits are used. So each bit has a weight associated with it. So these weights are 8421. So in other words, we say it's 8421 code. From most significant bit to the least significant bit. So we'll see this, the BCD codes. 0, I told you, the BCD code is nothing but the 4 bits. So 000, for 1, 0001. Likewise, till 9, for 9, 1001. So the BCD It ranges from 0 to 9 and it's a 4-bit code. So these are used to encode the numbers for output to numerical displays. So if we see this with an example, 9750, it's a decimal number. We are going to convert it into a BCD code. So for 0, we are going to write the 4 BCD code, 4-bit BCD code, that is 0000. And for 5, that is 0101. And for 7, 0111. And for 9, 1001. And then here we are going to see the Ascii code. Ascii code is nothing but American Standard Code for information interchange. So for a character digital, the binary code is this. And the hexadecimal code is this one. Next is the gray code. Gray code is nothing but a cyclic code. A circular shifting of a code word produces another code word. So that is what is the gray code. So a gray code, this cyclic code with the property that two consecutive code words differ in only one bit position, that is what is the gray code. So error detection code and the correcting code. So when we transfer the information from one place to the other place, so there is a possibility of packet loss, error take place. So in order to detect the error and to correct the error, we have the error detection and the correction codes. So along with the message, along with the information, we add the parity bit. We add the error detection code as well, so that in the receiver side, we can find it out whether any error is there. If any error is there, we can correct it. So we have two parity bits, that is odd parity code, even parity code. Here parity code is being attached along with the code, that is along with the information. So odd parity code, it counts the number of ones that is present in the code. If the number of ones present in the code is even, it allot the odd parity code, that is the parity bit, as 1 to make it as odd. If the number of ones that is present in the code is odd, okay, no problem. Odd parity code, no problem. The number of ones present in the code is already 1, so no problem. So what it will do, it will allot the parity bit as 0. So I'll tell you, this is the Ascii code. Okay, we'll see this one. If we count the number of ones, that is 3. 3 is the odd number and it is an odd parity code. So what it will do, it adds the parity bit as 0. Likewise, if you see here, the number of ones is 4. 4 is even. So we not to make it as odd, we add the parity bit as 1. So now if we count the number of ones, it is 5. So when we do this, in the receiver side, we can find it out whether any error is there, or otherwise the information has been received successfully. So at last, we have the Hamming code. So Hamming code, so in error detection and correction code, only a single bit error correction and detection is possible. Whereas in Hamming code, many, if 2-bit errors or 3-bit errors can also be find it out and can also be rectified. So I hope that you all have understood the various conversions, arithmetic operations, binary numbers, and then the binary codes. Thank you for watching. Thank you all.